The processor has a 24-bit system timer, which we also call as the Systick timer. And it counts down from the reload value, whatever you put the value to 0. Once the value reaches 0, it reloads or wraps to the value that is mentioned in the STK load register. That is the value that you want the Systick timer to count down from. And on the next count edge, counts down to subsequent clocks. So this keeps happening, this repeats. So say if the timer has a value of 100, it counts down to 0. And then once it goes to 0, it again reloads the value 100 and keeps counting down. And if you configure the timer to generate an interrupt, then at every countdown to 0, an interrupt is generated, which is called the Systick timer interrupt. Now this timer is native to the nested vectored interrupt controller of all Cortex M4 processors. So this is not vendor specific. This is common across all Cortex M4 processors. And it is mainly used by real-time operating systems for their tick interrupts. So real-time operating systems will need a tick interrupt or a tick to actually schedule and reschedule its tasks. So this is what this timer is mainly used for, besides a few other interrupts. Now the register details can be found on page 246 on the STM32 Cortex M4 MCU and MPU programming manual. I've just kept it here because it will be convenient for you to have a look at. So once you come to this slide, you will know where to find the registers. And when the processor is halted for debugging, so say you are in a debugging session and you have halted the processor, the Systick timer counter stops. It doesn't decrement. Here is a diagram of the Systick counter or timer, how it looks. So the timer, there are mainly 4 registers that the timer is controlled with. We have just shown 2 registers here, that is the reload value register and the control register in this diagram. So let us go through this diagram and understand how this particular timer behaves. Now you have the AHV bus on this end of the circuit. So you have the processor bus going into the clock, or the processor clock going into the timer circuit. Now the clock can go in 2 ways. That is, it can, whatever the clock frequency is, for example, if the clock frequency is 80 megahertz, it can go straight into the timer, or it can go via a divide by 8 block, that is divide by 8 prescaler. And whether it is going to be going through the divide by 8 or it is going to be directly connected to the processor clock is decided by this particular bit in the Systick register, which is the clock source select, and the register is Systick control and status register. So here if you put it as 1, then the value is, then the clock input is taken from the processor clock. Now if the bit 1 is that is the tick interrupt is set to 1, that is when the Systick starts generating an interrupt on every countdown. And then this is the enable bit for enabling the Systick timer itself. Now once we select one of the clocks here and we enable this, that is the Systick timer, this 24-bit down counter starts counting down. Every time it reaches 0, the value from Systick reload value register is reloaded here and the countdown repeats. Let us have a look at an animation of how this works so that it becomes more clear. So here we can see that we have we have a reload value. So now the reload value has to be 1 less than the count you want. For example, if you want a value of say 6, you have to load 5. So it is 543210. So thus you are actually counting down 6 ticks or 6 clocks with a value of n minus 1. So that is what is being shown here. So as you can see, the value of 5 is loaded here, and the value of 5 is also loaded in the 24-bit down counter to begin with, and then the value, there is a countdown happening. Once the value reaches 0, the 5 is reloaded again, and this repeats there. Now bottom side here, the moment it reaches 0, the Systick interrupt is raised if the interrupt is enabled. So at every 0, the interrupt is raised. So what happens? The counter is counting down to 0 and the interrupt is getting raised. So this is how the Systick timer works. Now, how do we calculate the Systick timer reload count? It's quite straightforward actually. So if we go back to the diagram of the Systick timer, and let's assume that we are having the clock directly fed into the timer. So obviously the frequency of the timer is the same as the frequency of the system. So if it is set at say 84 megahertz clock, which we will be working with, the period for one clock cycle is about 1 over 84 into 10 to the power of 6. That is that many seconds. Okay, so if that is the period of one clock cycle, that many seconds, so say if we have to have the timer for say 5 milliseconds or 10 milliseconds, we need to divide what the milliseconds that we want by the time taken for one clock, and that will give us what should be the value that we should put in the reload register. Now mind it, this is a 24-bit down counter. So with a 24-bit down counter and a 84 megahertz clock, it will be not possible to have this counter generate an interrupt every second. So in that case, we will have to slow down the counter or the timer, and thus we will need to pass it through the divide by 8 prescaler block. So the 84 megahertz clock that we are feeding in becomes 84 divided by 8. So the Systick timer is seeing a much slower clock. So in that case, we can have the timer count bigger times. For example, you can configure the timer now for 1 second and so on. So we will see the calculation here in this slide. So whatever we spoke about, if the timer is fed from the system clock and we need the timer to overflow once every second and raise an interrupt. So assuming the co-frequency is 84 megahertz as we discussed. Now one Systick count is equivalent to 1 over 84 into 10 to the power of 6 seconds, which is the same as the clock speed of the controller. So we have selected this value 1 here. So the clock source select is 1 here. Now the Systick count has to be, now for us to have and 1 second as the timer interval, we know that whatever count we find out here, it has to be 1 less. So one Systick count is equivalent to 1 over these many seconds, which is the same as the clock speed as we discussed. Therefore the Systick count has to be this much minus 1. Since we need to have one count less in the reload register, which is this value. So I just calculated and I have put this value. And the problem here is this is not a 24-bit value. This is a bigger value. Okay, so if you see 4 4s are 16, 17, 18, 19, 20, 21, 22, 23, 24. So this is like a 27-bit value, and this is a 24-bit register. So with an 84 megahertz clock, it is not possible to have a 1 second timer overflow. That is, the timer overflow of 1 second is not possible. So what we can do is we then need to use the divide by 8 prescaler, so that value becomes this for the load register. So this -1, of course, this -1. So this is the value, and this value can be put into the load register. So, and of course, if we want smaller time periods, say 5 milliseconds or and so on, then we can use the 84 megahertz clock, because that there the count that you are putting into the time load register is much lesser. The calculation is generally this: the desired time in seconds over time for one processor clock cycle. Okay, so in this case, time for one clock cycle is 1 over 84 into 10 to the power of 10 raised to the power of 6. And if it is a divide by 8, then this time becomes higher. This time becomes higher. That is, time for one processor clock cycle becomes 8 times the value. Okay. And so the count here is 0x6689F. So you can try out a few calculations here, give it different times. For example, you want 5 milliseconds, you want 15 milliseconds for different clock frequencies. Do the calculation in hand and see what counts you get. That will be an interesting exercise for you.